Let's define the meaning of a sequence. A sequence is an infinite ordered list of real numbers, say a1, a2, a3, and so on. Formally, a sequence is a function a from the natural numbers to the real numbers, where n is mapped to a subscript n. The sequence a1, a2, a3, and so on is equivalent to a function a from the natural numbers to the real numbers because it is determined by its values over all natural numbers n. We will denote the sequence by bracket an, where n is a natural number, or simply bracket an. Note that the sequence an is not equivalent to the set an, where n is a natural number, because the ai's are in order and can be repeated. Let's see some examples of sequences. First, we have the sequence an equals 1 over n. In other words, the sequence is 1, 1/2, 1/3, and so on. The second example is an equals 1 minus -1 to the power n all over 2. In other words, the sequence is 1, 0, 1, 0, 1, 0, and so on. The third sequence, we define a1 equals a2 equals 1, and for all n which is greater than or equal to 3, we define an equals an minus 1 plus an minus 2. In other words, the first two numbers of the sequence are defined to be 1, and every next term is equal to the sum of the previous two terms. This is known as the Fibonacci sequence, and its first few terms are 1, 1, 2, 3, 5, 8. The fourth sequence is equal to the sum of 1 over I, where I equals 1 to n. This is the sequence 1, 1 plus 1/2, 1 plus 1/2 plus 1/3, and so on. For the fifth sequence, an equals n over n plus 1. In other words, the sequence is 1/2, 2/3, 3/4, 4/5, and so on. For a real number a, we want to rigorously define an converges to a as n tends to infinity, or a is the limit of an. In symbols, we write an tends to a. The idea is that an tends to a if an gets closer and closer to a, but not necessarily momentarily. For example, consider the sequence an, which equals 1 over n if n is odd, and 1 over 2n if n is even. As n tends to infinity, an gets closer and closer to 0. But the problem is, an also gets closer and closer to -1. So we want to say that an gets arbitrarily close to a. In other words, an gets within epsilon of a for any epsilon greater than 0. This epsilon greater than 0 represents the distance between an and a. Now it's useful to define the following. A real number b is arbitrarily small if the absolute value of b is less than epsilon for any epsilon greater than 0. The second idea of the definition of convergence is as follows. An tends to a if for n which is sufficiently large, the absolute value of an minus a is arbitrarily small. This means that once n is large enough, the absolute value of an minus a is less than epsilon for any epsilon greater than 0. However, this implies that an equals a, because otherwise the absolute value of an minus a is greater than 0. So if we take epsilon equals 1/2 of the absolute value of an minus a, then the absolute value of an minus a is greater than epsilon, which is a contradiction. To fix this problem, we want to specify epsilon before n, so that n depends on epsilon. In other words, to get arbitrarily close to the limit a, in other words, the absolute value of an minus a is less than epsilon, we need to go sufficiently far down the sequence. In other words, the n is large enough. Then, if epsilon greater than 0 is changed to a smaller value, I simply go further down the sequence, in other words, a larger n, to get within epsilon of a. This graph shows the idea of convergence in this definition. The crosses represent the terms of the sequence an. If we consider epsilon 1, then an is within epsilon 1 from 0 for the second term onwards. However, if we consider epsilon 2, which has a smaller value, then we have to go further down the sequence, or more precisely, at least the fourth term, to get within epsilon 2 of 0. In general, there is no n sufficiently large that works for all epsilon greater than 0, but for any given epsilon, we want there to be an n sufficiently large such that the absolute value of an minus a is less than epsilon. So we consider the definition. For all epsilon greater than 0, there exists n, which is a natural number, such that the absolute value of an minus a is less than epsilon. This definition is bad, because the sequence an, which equals 0 if n is even, and 1 if n is odd, satisfies the definition, but an oscillates between 0 and 1 instead of converging to 1. Thus, we need to modify the definition to require that the absolute value of an minus a is less than epsilon, and it stays that way. Now we can formally define the convergence of a sequence. An converges to a if and only if, for all epsilon greater than 0, there exists natural number n such that little n is greater than or equal to n implies that the absolute value of an minus a is less than epsilon. This means that however close, represented by, for all epsilon greater than 0, I want to get to the limit a, there is a point in the sequence, represented by, there exists n, a natural number, beyond which, represented by little n greater than or equal to n, an is indeed that close to the limit a, represented by absolute value of an minus a is less than epsilon. Note that little n is greater than or equal to n implies that the absolute value of an minus a is less than epsilon, is equivalent to for little n greater than or equal to n, the absolute value of an minus a is less than epsilon.